Greetings, Earth enthusiasts. If you ever wondered about the incredible perspectives our planet has to offer from high above, you're in the right place. I am Dr. Clive Coetzee, and I'm thrilled to be your guide on this captivating journey into the world of remote sensing. Welcome. And please remember to like, subscribe to, and share this video. Thank you.
I received some very nice and complimentary comments for the last two videos that I made, the ones that I made yesterday, the two in pursuit of urban heat maps of urban hotspots, which I'm very grateful and thanks. We gained another 7 subscribers over the night since the posting of these two videos. So please, we are 6 away, 6, only 6. I need 6 clicks of 6 presses or whatever you want to call it. So please press those buttons. I need those 6 to get to the 500. Then I'll have a what will I have over the weekend? A nice cold beer, I think, to celebrate, or a nice glass of wine or something to that effect, if I can get to 500. So what's that movie? Go Ahead, Make My Day. What was that movie? I can't remember the movie's name. Anyway, was it Clint Eastwood or Arnold Schwarzenegger? We in the movie said, "Go ahead, make my day." So let me say it, please. Go ahead, press those buttons, make my day. Anyway, enough of that. Let's continue. So we were busy with this urban heat map or urban hot spots or urban islands. I think there's 3 words for the same thing. Anyway, and yeah, so we estimated, or we identified and highlighted our so-called urban area using the land surface temperature anomalies for my region of interest. So there was a couple of interesting things that stood out there. Let's quickly go there. There was a couple of things that stood out here that I think we need to look a little bit further. Is, remember, I always do when we do urban stuff, I always use winter. So let's run it and see what happens when we change it to summer and see what happens. So just to get a mental picture of our urban heat map, there it sits. So maybe what I need to do is just make it a little bit bigger. And let's take a snapshot, print screen, and let's file, new. Let's just add it in here. So that would be our winter. Okay, so that would be our winter. So if we do a summer, let's see what that looks like. So that's just for comparative purposes why I'm doing that. Okay, so let's quickly run it. Remember, when we're going to run it for summer, there may be some other stuff that we have to, variables that we have to change. So for example, our minimum or maximums, we most probably will have to change, etc., etc. So just bear that in mind. So let's quickly do that. Let's do it for 23. So that would be, let's say 12, and then that would be 24. Let's hope it runs through, and that would be 2, 4. So that's the peak of summer. Okay, so that's going to be very dry, very little vegetation, temperatures 35, 37, peak the temperatures closing to 40, etc. So let's quickly run that and see what that looks like. You can see there the temperatures much higher. Remember, the winter was 20s, 20, 21. You can see there 36, 37. So, and you can see the 1%. The difference in the winter between the mean and the medium wasn't much, but you can see the difference between the summer mean and medium is quite high. So that means even higher outliers. So let's have a look and see if we take all these away. And there's our urban hotspot. Now that does not look closely, remotely the same as in the winter. Not even close. That's what I'm saying. It doesn't reflect. It doesn't reflect the urban side of the region of interest at all. Anyway, let's make sure that our data is correct. So for example, if you look in the maps, the images, the mean, median, and mean images, you'll see they all are just red. And that's simply because these numbers, you can see these numbers, is not close to the actual numbers here. So let's make this 30, and let's make that 40. And that should cover how interpret. So our map images should look much better now. So, okay, so let's continue. So that's what I'm saying. Once we change this, it's not a simple change one and the rest falls in place. We need to make sure that we are consistent in our script. Okay, so that should sort out that. There's nothing here in terms of that. There's nothing there. Visualize it. Again, I'm going to make it 30 to 40. That should cover that. And I think, okay, here again, it is 30 to 40. And again, this is, we can use our inspector to get these numbers if we're not sure. These were all the same. That's the same. Okay, now our urban thermal variance index. Now let's quickly just use our inspector at any place and get an understanding of that number there. 0.03, so that should be okay. Let's look another number there. Just to make sure that our numbers, that's 0.07. So that's within that. Let's have a look at that value there. So I'm just arbitrarily just selecting locations to get understanding what the numbers should be like. It's minus 0.22. So that's, so I think that's okay. So let's try now. That's quite different from here. 0.04. So let's keep it like that. Let's keep it like that and see what happens. And then obviously the big one is going to be when we okay, standard deviation. That should be nothing strange there. Obviously it comes now to this portion here. When we do the graderize, we will play around with that number. Standard deviation that. Same with the hotspot 0.0. Okay, so let's run it. Let's see after those changes whether we have you can see still. And so I don't think we need to go anything further. It's not going to make any difference because you'll see what's happening here. And so this cannot be urban areas. You can see that this is simply not urban areas here. If I put it on a satellite. And let's take it away. You see all the high temperatures are here, which makes a lot of sense. And I'll tell you now why this is not going to work. You can see there, it is these areas here. It's not going to work. And you see there's no buildings there. This is all, you see this is now again I should actually have, the satellite is now a winter satellite image. But this is agricultural land here, farmland, which is green in the summer, but this basically turns to sand, to bare soil in the summer. So that's why it is typically there. So this is not going to work because we run into the issue of summer. And also the other thing is that in summer, the closer you, obviously, this is the Atlantic, so this is very cold water. So in the summer, there's lots of wind which comes over this cold water. So that's why this area typically is colder than the inland areas in summer because of the wind that comes through the Atlantic Ocean. Obviously, in the winter, there's very little wind, and therefore it's much more accurate. Okay, so I'm not going to even go further. So the point being is that it's not going to work, not even close. So let's go back to our winter. And it was our winter time again, 5 to 10. And that was 10. I must just remember now to change it back to, what was it, 17 and 28, if I can vaguely remember. Well, we know it here. It was 17 and 28. Where is it now? Why is my... Okay, we don't put it here. 27. I'm just going to 28. So that's what I'm saying. Winter is not going to work. Summer. It's not going to work because we run into um, 17 and 28 because we run into this issue of the bare swells. Now, if you don't have bare swells, if your region of interest is unaffected by bare swells, then by all means, go for it. By all means, use the summer period and let's see what happens. But as I said, it's very clear that in my situation, given the location, given the dynamics of winter versus summer, it's not going to work. So first point here is that the urban heat maps, or the effectiveness or the efficiency of it, greatly depends on the time period and or the seasonality, and then the structure of your region of interest, the characteristics of your region of interest. So that's very important. Okay. Then I think the other one that we wanted to do is to see, because remember we used in our thermal field index, we used the median numbers. We used the median numbers. And I wanted to see what would be the mean numbers. What would that look like? So the mean numbers. So here we have the median. So let's do the mode of the mean, which is mean. So let's do that mean. And is that lowercase or higher case? Uppercase. Average. Average LTS mean is as lowercase. Just want to make sure, and mean. So let's run it. I don't think, because the mean and the median is so close together, I don't think we're going to need to change any of the visualization parameters, etc., etc. So let's keep that the same. And remember, that was our hotspot there. Let me just confirm. Oops, see, that was our hotspots there. That was our hotspots there, and let's run it again. Okay, let's run it. Let's have a look and see what that looks now. So I'm just going to unselect these because we don't want to run that. See what it looks like. And that is okay. So let's quickly take a snapshot. I just want to make it a bit bigger. Take a snapshot once it's loaded, and let's quickly put it into my Word document, and let's compare it. And there's definite differences. You can see in the median, there's much more hotspots here to this northern side than when we use the mean. And the mean seems to be similar for the main city area. And again, a little bit less here, a bit more there. So there's some subtle differences. In the main, it's very similar, but there's definitely some subtle differences between using the mean numbers in our hotspot or in our heat map versus versus using the median. So that's that is IUTF, etc. Okay, that's hotspots. Okay, so there's definitely some differences between mean and median, but not massive. So I would, okay, that's up to you. I think this is for them in this case. As you guys know, I love the median reducer. I'm not a big fan of the mean, um, but in this case, it seems like the mean is more accurate in that it does exclude some of this bare soils here. That would be my reason why I'm going for the mean. So save this. So in my instance, the mean seems to be a better indicator or better predictor or estimator of urban hotspots or uh, heat islands, urban heat islands, compared to the mean. So I would stick with the mean. But again, and we can do the sum or the minimum. That's another options we can do. We can use those reducers. Just in our case, we just have to calculate the mean or the mean or the maximum average minimum number or maximum number for our whole region of interest, so that we can implement that in our urban thermal field variance index. So just bear that in mind, that in this case we have calculated the mean and the median, average, mean, and median for our whole region of interest, which we obviously use, but we can use the standard, the minimum and maximum as well, but we just need to, yeah, make sure that those numbers are defined. So definitely point one, number one, summer is out. It's not going to work, not for this region of interest. Again, because of the soil. As I said, summer, all this agricultural land is fallow, standing empty, no vegetation, baked in the sun. Not good, not good at all. So summer is not going to work. However, the mean statistic seems to be a better estimator than the median statistic. So that would be sort of in summary when it comes to this specific piece of script. Okay, so what I've also done is in the following script is to calculate what we call a land surface temperature anomaly. Sorry. And that looks something like that. Okay, which is also can be used as a predictor estimator of urban heat islands or urban heat maps or hotspots. So in essence, we do the same as what we did in the previous tutorial. There's our urban field variance index. So up to that, we've done exactly the same. So there's our time period. It's just a little bit where we have it next in a horizontal. Here we just have it in a vertical format. So roughly the same. We're clipping image, and we have our data set. So exactly the same. Nothing changes. Load our data set for our time period. Okay, so we load our data. So remember, it's clipped now already. Now we load it for our data for our period, which is this period. Let's make sure it's the same. Oops, it must be 4. 4 to 10. 4 to 10. Let's run it. Sorry, let's run it. So that's exactly the same. Now I'm calculating various statistics for my region of interest. So remember in the previous one, in this one here, we've calculated the mean and the median. The mean and the median statistic for my region of interest, for the whole region of interest, which is 20.58 and 20.09. Okay. Now, in this case, I'm generating 4 statistics: median, mean, max, and minimum. And there they are. The maximum temperatures, 25, mean 20.06, 20 point mean is in this case 20.5. I'm not sure why there's this a little bit of difference. Maybe it's just because of the structure of the code itself, but it should be exactly the same. There shouldn't be much of a difference. So I'm not sure why there's this difference. I don't know why there's medium composite. Oh, we're using, yeah, but you see, okay, we're using the median composite median, median composite median, mean composite mean, mean composite mean. So I'm not sure why there's this difference, but there seems to be a difference. So I'm not sure why there's this difference. See, we're doing the mean. We're using the median. Okay, so this is where this is. No, but it's still median and the mean. Oh yeah, here we have the mean composite and the mean. Okay. And here we have the median composite and the mean of the median. And that's why there's this difference. Okay. Understood. Understood. So, yeah, so we're generating the reducer. That's the image. Sorry, this is the image that we reduced, not the statistic. Here we reduce the image, i.e. this one here, because remember there's the image collection. So we reduce that image collection with 5 or 6. So we have generate now a median image, a mean image, a max, and a minimum image. So we're generating 4 images. And there they are. There's your mean image, median image, your mean image. This is the maximum image. It's going to be much more red, I would assume, at some point. It's going, yep, much more red. Almost the whole thing is red because we have the same um, visualization parameters. You see the maximum is close to 28, which is all red. And the minimum is going to be 13, which is just going to be blue because it's less than the 17. So we actually have to create different visualization parameters for the maximum and the minimum. You'll see they don't put in. Or we have to change this to something like 12. And we'd have to make this, let's say, 30. Let's run it in the meantime. Let's try it again. Okay, so that's just playing around. So, sorry, this is for my image. Okay, so this is not generating the statistic. These statistics, okay, it's not generating them. It's just generating these images. Okay, we add the images. Here we're actually generating the statistics. Here we're actually generating the statistics. And that, in this case, it compares to this, and this part here, where we generate the statistic. You see here we generated a mean and a median. So we took the median image, sorry, a median image, and we created a median. So that's that one. So that median is derived from the median image. The mean is derived from the mean image. Okay, so that's why we get these numbers. Now you can see here, in this case, we use the median composite, okay, not the mean. So in this case, if I change that to this one, to median, and then let's quickly see median and the mean there, then I should get the same number. I should get 20.06. And there we go, it's 20.06. Okay, so that's where the difference lies. So let's just go back to mean. Okay, so that's where the difference lies. I hope that makes sense to you. So in this case, we're using the median image, not the mean image. And from the median image, we're generating the mean, standard deviation, minimum, and maximum for statistics. And there they are, maximum, minimum, min, maximum, mean, minimum, standard deviation. And that is based on the median image. Okay, it's easy to get confused, huh? It's very easy to get confused. So please stay with me. Please stay with me. Yeah, so I hope that makes sense. Okay, so these are the images for the average images of the single statistic for my whole region of interest. The maximum for any of these locations is 25. So there's no location that recorded a land surface temperature more than 20.21, 25.21, etc. I hope you get the idea. Remember the scale, eh? Scale is very, very important. And there we've got our thermal, okay, which is exactly the same as previous. It is, in this case, the median subtracted by the mean divided by the mean. Okay, so we're using the median composite again, and I'm using the median mean. So nothing, and I present it, I create my greater than so that I can mask. I calculate my, okay, so up to here is exactly the same. Nothing different. Well, not nothing different, a little bit different in terms of our statistics, but in general, the same things. Now here is when we do the anomalies. Okay, so here we calculate the median compensate, because remember we work with the median image. We can change that to mean or to maximum, because remember here they are. Here's the composites. So there's the median compensate is the reducer, the median reducer. Okay, so we use that. Then we select LST and then subtract the mean of that. Okay, so we take each median value here. So each of these pixels have a median value, because that's the median image. And we subtracted them this mean value of 20.06. And we don't divide, because remember the urban field variance index, we divide. You can see, so subtract. So it is not dividing. Okay, so that's the big difference between the urban thermal field variance index, again me and this bloody number or thing, and the anomalies is just that we don't divide, and therefore the minimum maximum values will be a little bit different. So that is just basically creating a land surface temperature anomalies image. Is when we just take the image and we can take the mean or the max, we can subtract it by difference, we can play around with this. But in this case, we use the median image, subtract by the mean. Single, remember, this value is a single value, which is that value for everything. So we take each value's median, each pixel's median land surface temperature, and we subtract it by this mean number. And that's what we get our land surface temperature anomalies. And that's just basically blue. On the cold side, on the non-urban side, white sort of neutral, and the red is sort of urban. And you can see, to some degree, it also closely matches. Okay, it also closely matches what we have in our hotspots. So there's my hotspots. To a large degree, it correlates to our urban hotspots. Remember, there's our urban thermal, whatever. And you can see it sort of correlates to that. So it's just a small, subtle deviation from this urban thermal field variance index. But again, something that potentially we can use. I'm not going to do this for summer because I know the whole thing will be red, or this part here will be red. So this is potentially something that we can do as well. And then the rest of the script is basically just to generate a time series. Now, it's exactly the same as the time series here. All we've done is to add a trend line. And then we've created a histogram, which is exactly the same as the histogram there. So in that case, it's nothing. Then we just added this little title map here, a title chart here. And we just put in a, what do you call it, a legend. We just add a legend here and this here. But in essence, it's exactly the same as the previous script, where we calculated the hotspot, except here we also included this idea of anomalies, land surface temperature anomalies, which is different to where there's significant difference from the mean number. And so that's it. So again, the whole idea is to see in which form or structure we can use this method to correctly identify and visualize build-up or urban areas compared to non-build-up, non-urban areas. Because what we want to do is to see how towns or cities have evolved over time and stuff. So that's really what we want to do. But anyway, okay. So another way of doing urban heat islands or urban heat hotspots or just hotspots or whatever you want to call it. And there we go. Yep. So there's two options. Either divide or just keep it. This idea of the urban thermal variance index versus the anomalies. And or I would suggest do both of them. And then mask those areas out, because we can mask this now to say if it's greater than a certain, then mask it, and potentially it will nicely overlay or correlate with one another. Okay, so yeah, I think that's it what I want to do on this particular video tutorial. I think we've covered everything. As I said, the last part of the code, there's a lot of it. It's just for these semantics. But as I said, I very seldom include these things in it because what I normally do is once I've done this in Earth Engine, I simply just export these images and charts and stuff to my other programs, i.e. Excel, Geoda, RStudio or QGIS, and I do the work there. Yeah, so I don't very sell. It's just I think it's unnecessarily. If you want to display it, present it as is within it, yes, go for it. Then it looks nice. But yeah, there's there's too much that can go wrong with these things, and it messes up everything. Anyway, that's a personal preference. I leave it up to you. Okay, so that's just quickly a continuation, some bit of variance, bit of playing around with our standard urban heat map idea, heat island idea. Okay, cool. So with that said, I'll yeah, let's keep in touch, please. Yeah, again, I appreciate all your kind support and kind words over the last day or two. It really means you just give one oomph, just gets one going and gets one keen to do this again. So let's grow this channel together. If you like what I do, if you like the channel, you find it useful, you find it informative, please like, subscribe, share, comment, hit that notification bell, etc., etc. You know what to do, and I'll figure out who said it, whether it's Clint Eastwood or um, Arnold Schwarzenegger. Make my day. Okay, cool. I'll see you on the other side.